That discussion we'll have in detail on Thursday. Actually, probably at the end of Tuesday when Mark comes in. You can actually ask the expert. I consider him to be the expert. You can ask him those questions, and he'll be able to answer those. So exceptional flow control is what we're talking about. So up until now, there were two mechanisms for changing the control of flow in your program. There was the jump instructions and the conditional branches, and then there was the call instruction for function calls. So both react to changes in internal state. Internal program state allows you to do your branching. But this is insufficient for a useful system. You need your program to be able to, well, your operating system and program to be able to react to changes in external system state. So, for example, a packet arrives over the network. How are you going to handle that? Your program's not going to sit there and poll the network interface for a packet. What happens if a user hits Control-C at the keyboard? Like, for example, in your binaries, you Control-C out of your binaries. How is that handled? Or if the system timer expires. Or if you have something like division by zero in your program, how does that get handled? How do you send a signal to terminate a program? So to do this, we need a separate mechanism, and that's what this chapter is about, exceptional control flow. And this is a really nice segue into your operating systems class, which is hopefully a class that you're going to take next quarter. No. So the best sequence is 333 following 201 almost exactly, because then this is the handoff. But refresh yourself with this stuff before you take 333 in the fall, unless you take it next quarter. Okay, so exceptional flow control. This is defined as changing control flow in response to a system event. There are several mechanisms we're going to look at. There are exceptions and interrupts. And then higher level mechanisms, context switching processes, which is similar to, it's done with an interrupt. And then signals, which are basically process to process exceptional sort of control flow. We used to cover non-local jumps, but this is not recommended that you do anymore in your program, so that's why the big line is across it. Ignore the section in the book. It's great. I tell you to ignore it, and I bet you a lot of you would be like, oh, what is it? Don't do it. What was it? It's I'm in real trouble. I need to do over. They don't like that. Yeah, it's not a good thing. Hard to reason, really hard to reason about what's going on. So, exceptions and interrupts are the first thing we're going to talk about. To give you the context, here is what the real system looks like. Up until this point, we were looking at the processor and the memory, pretty much, and then the set of registers inside the processor. But over on the right is everything else. And we need to build a complete system. We need to be able to integrate all that stuff. So when anything happens on any of these devices, you need to be able to tell the processor, hey, got something for you. And that's what this interrupt controller is. It's sitting here on this bus, an I/O bus, and it says, you know what? One of these 7 things needs some help. And then the processor is going to interrupt whatever process is running, and we'll run a handler inside the operating system that's going to go and do something for that, service that device. So that's what an interrupt will do. So the idea functionally is to transfer control from the program, from user code, over into the kernel code in response to some event. And so typically, this will require you to begin to move from user-level execution over to kernel execution or supervisor execution. So you'll end up setting the supervisor bit and then executing kernel code to do whatever it is you need to do to handle that exception. Okay. So here is an animation. You have your user code. It's got its program counter here. This is where it's currently at. You get this event. It triggers an interrupt, and in response to that interrupt, you have a facility that will take that sort of exceptional event and then call the appropriate kernel code to process that event. And then after that handler has been run and the data has been taken care of, you eventually want to return back to the program that was running before. If it turns out the program itself generated the event, like divide by 0, then you could potentially abort the program. If the program caused the exception through something that, for example, its memory read faulted, like the page, the location in memory that it's trying to read wasn't in the cache or wasn't in main memory, had to go off the disk. If it's the case that it can recover from that, then you would send this back to the user code at the instruction that it was executing. Okay, so those are your 3 options. And we'll go over each one of these. So how is this implemented? Well, as it turns out, there's a hardware register in x86. It's called the interrupt descriptor table register. And every process loads that register with a virtual memory address that points to a table of function pointers. So this table has an entry, and it's much like a switch table. It has an entry for each kind of interrupt. So every interrupt that interrupt controller, every interrupt is associated with an interrupt number. And that number is used as an index into this table of function pointers. And for each one of these function pointers, you'll end up going to places in memory that has code that will handle that specific interrupt. So if it's a video card interrupt, then this will point to something that the video driver will be able to execute and handle whatever event is there. So, questions about that? Straightforward? Yes.
Sounds like that's a very, like that could have some really bad ramifications, right? Like you can hijack the code for the interrupts. You can hijack the code going back into the.
You can hijack that
Yeah,
with the register instruction.
Yeah, but you can also hijack like the stuff going back to your code, like back to their code. Say, oh, I want to go back to this other function instead of where you were.
So take my malware class. We'll talk about how bad guys are looking at this and saying that's what I can modify to get access.
Is that what the last like the last 2 out of the CTFs that we did was all like signal based? So is it kind of playing around with some of this stuff?
That one not in particular, but definitely in the malware class you're looking at ways of hijacking function tables, and this would be one of them. Okay, so what I just described to you are asynchronous exceptions or interrupts. So these are events external to the processor, and you basically indicate the fact that an event happened by setting the interrupt pin on the x86 processor. And then that will in turn cause the associated handler to run. All right. Examples, the timer interrupt. So every few milliseconds, an external timer will trigger an interrupt, and this will allow the operating system to wake up and say, do I need to run a different process, for example? So the timer interrupt, the timer tick, for a scheduling event is typically done using this mechanism. Okay. Another one, I/O interrupt. So Control C at the keyboard or any keyboard key strike will cause an interrupt handler to run. And then packets in the network and the arrival of data from the disk. Okay. The next set of exceptions are the synchronous ones. And these are caused by events that are the result of executing a program instruction. Okay. So this includes intentional ones, like traps. So, for example, system calls are trap instructions. You say, hey, I want to go into the file system and open a file. Eventually, you get to a point where, hey, I need to actually hand this over to the operating system to process. Well, in order to synchronously call into the operating system, you have to issue a trap, an intentional exception. Another one is if you're in the debugger. So you guys have all been in the debugger and you want to set a breakpoint. That's inserting an intentional interrupt into the code, in hex 3 as it turns out. And that will synchronously cause the exception to run that will then return control over to the debugger. The debugger is the interrupt handler for that synchronous trap. You can think of it. So, all right. With these traps, when they return, the return will go to the next instruction after the instruction that just executed, the interrupt, the trap instruction. Another kind of exception is the fault, and these are unintentional, and sometimes they're recoverable. So if it's a recoverable fault, then you will return to the instruction that caused the fault. Because that instruction failed, but if you execute it again, after, for example, the memory gets loaded, it will execute successful. It'll work. Yeah. So page faults are recoverable, which is what I just described. Protection fault is not. So if you dereference a null pointer, that's a fault, not recoverable, and it'll abort. So those are the three kinds of outcomes with an exception. Yes.
Can you write a recoverable methodology for dealing with a null pointer?
Yes. In fact,
so you can make unrecoverable execution faults recoverable.
Some of them, but there are some that are uncatchable. Actually, aborts. So aborts are both unintentional and unrecoverable. You cannot catch these things. So examples are hardware errors, like machine check or parity error in your memory. Then rather than continuing on, like PHP would, it says, no, this whole thing is broken. In fact, I might have to reset the entire system. That would be the unrecoverable. Yeah, so unrecoverable. So aborts the current program, game over. It's like, I can't, you don't want me to continue sort of thing. Fail safe. So imagine that. Right. So here are some examples of exceptions classified by their the kind.
That's ironic.
So divide by 0 is exception number 0. It's a fault. Page faults are 14. Machine check, system calls or system traps, 128, etc. So we'll first cover traps. And these are the synchronous intentional exceptions. So oftentimes your program will want to call operating system code. For example, it needs something in the file system, it needs to set up a new network connection, these sorts of things. And to do so, there is a special trap that the compiler will compile into your program or compile into the library code that will call the system call instruction. So there are two ways of doing this. An int hex 80, which is interrupt 128, as we saw here. This is the system call trap. Or you can call the syscall instruction explicitly. And then what you do is you specify which system call you want run, and that would be passed in a register. So you load the register up with a system call you want to call, and then you call either int hex 80 or syscall, similar to like a function call.
Oh, okay, that's what I was going to say.
So somebody could reverse engineer by just running through the code and then seeing, oh, in my REX register I'm passing this, so look at this code and see if that's been altered, if it's like a malware or something.
You can figure out all the system calls that malware is trying to access by this, right? So if it is going to do an exec, or if it is going to do a read from a particular file, you just have to parse the sequence of calls that lead up to the actual int hex 80, and then you can see it'll uncover the behavior. So reads, writes, open, close, those are all file system things. If you want to create a new process, you can fork, and we'll talk about fork later. You can exit, called the exit system call, or kill other processes with the kill system call, which we'll get to later.
Is that so? In one of the CTFs as well, we use kill to actually send messages to other system calls.
To other processes.
To the process.
Yes.
Sorry. So that's another. So it's kill both a system call and a
user utility. So they overload the
Okay, I just thought I'd ask.
And the kill user command will call the kill system call, or the kill library call, which will call the kill system call. So yeah, it's name overloading. Okay, so here's an example. So in the standard C library, you have this open call to open a file, and you give it a string, which is the file name, and then some options, which is basically an integer with those flag fields. And then in the library call, if you disassemble libc, you'll see something that looks like this, where you move hex 2 into EAX, and then open is actually system call number 2, and then you call syscall or int hex 80, and then you check the return value. If it's negative, that means the open failed. So that's what this assembly code snippet is doing. All right. So RAX contains the system call number, and then the arguments are similar to the arguments for x86-64, except after Diane's silk dress, it cost her, way more. 10, 8, and 9. So slightly different. But you probably won't ever need to reverse engineer a system call unless you're really deep into security. Okay. So that's what is there. That is the same code. Okay, so this is what happens in your user code. You're going to call the standard C library open function, and that's going to bring you to this part of the code. And then as soon as you do this syscall instruction, this will trap into the kernel. In the kernel code, it will go through the code to open a file in its file system. So all the file system data structures are in the kernel, and to navigate to which file that you're actually looking to get, it has to traverse the directory tree. So the directory tree is some data structure in the kernel, and it's going to figure that out. Once it's opened the file, it's going to return to you a single file descriptor, an integer, that you can then use to read and write whatever data you want. And so this will return directly to this compare instruction, and then you can operate on that file descriptor after that. Okay. Questions? Yeah.
EAX, the function, the syscall operating register.
That is the return value. So it's a system call number that you pass, and then it's the return value coming back.
Yeah.
Yep. Okay. Here's a fault example, and this is a recoverable fault, a page fault. So if you have something like this on the right, and if you've allocated a whole bunch of memory for this integer array, and all of a sudden you're freshly going to access A of 500, it might not actually be in memory. It might be sort of stored really deep in the memory hierarchy. And then in order to get that into the cache, it takes a long time. And so rather than sit around and wait for that synchronously, this will cause an exception, a fault. And then what happens is the operating system will pass control. It'll issue the commands to try and load that memory location into memory, but then it'll issue it a command to load a different process, or it'll context switch to a different process typically. And so here's an example where you're going to assign 13 to this memory location, and let's say that thing faults. This is what it looks like. On this moveL, this thing is going to generate a fault, which is an exception, a page fault exception. And then the kernel is going to implement the code that will retrieve that page from disk to memory. If you swapped all the way out to disk with the swap file, and actually that comes in operating systems, if you don't have enough real memory to store the memory image of your program, then it gets swapped into disk. And then that data is stored onto disk. It's separate from the file system, but it's stored in this special swap file on disk. That's what we're talking about here. And because disks are really slow, you would initiate the sort of instructions to get that page into memory, but then you would go and the kernel would be able to do something else. Eventually, it would be loaded into memory, and then you could return, and you would end up re-executing this moveL. Because now you don't want to go on to the instruction after this, because obviously you didn't finish this instruction the first time, and then hopefully it's successful on the second. Okay. Another example is the segmentation fault. So here again, I access an array element that's way beyond the end of this array, and so if this address isn't valid and you execute this instruction, the operating system, if this is not a valid address, it will generate this segmentation fault. And so this is what it looks like. You get to this move-L. There's a page fault. It tries to see if it can bring this in from memory, but it's an invalid address. It goes through the operating system tables and it's like, there's no address like that anywhere. And then in this case, you signal the process with this segmentation fault, which I did catch on some of your binaries. This is a catchable one. But typically, the default is to send a segmentation fault, segmentation error signal to this user code, and then it would exit. It would abort, usually. Okay, so the next thing is process context switches. So if you remember what processes are, these are instances of your running program. And so there are two abstractions that a process will give you. One is a private address space. So each program believes it has exclusive use of the entire main memory region. The other thing is a logical control flow, so a sort of a thread of execution is what it gives you. And that this allows that program to appear to have exclusive use of that CPU. So how are these illusions maintained? Well, as it turns out, exceptions are instrumental for making this illusion work. And I'm gonna go through a walkthrough of exactly what goes on. So the illusion that the operating system wants to maintain is the one here, where every process, and this is a single process here, every process appears to it have everything, have both all of memory and all of the CPU, and all complete ownership of the hardware registers. And so how does this actually get implemented? Well, as it turns out, the CPU can only run one of these at any given time. There's only one yellow box at your disposal. And so the illusion is maintained by the processor continuously switching amongst all of these processes seamlessly. Okay. So the way this works is through a operating system mechanism called a context switch. So it's managed by the operating system kernel. And here you have two processes, A and B. You have process A is running, and it's really expecting to own the entire system. But the operating system all of a sudden gets this timer interrupt that says, hey, you know what? I don't want you to starve every single other process on this system. I'm going to interrupt this program, process A, and then I'm going to run a scheduler, a scheduling algorithm. Do I let A continue? Or maybe I want to swap in B, who hasn't seen an execution in a while. And so as part of this kernel code, if it decides to schedule B, then it will swap out A. There will be a context switch from A to B's context, and then B will be able to execute.
That's like the shadow registers, right? Like it's switching shadow registers.
It can be implemented as shadow registers. Typically, this has been implemented in memory. So way before shadow registers and hyperthreading, this was all done in memory. And so this is the pre-shadow register implementation of context switching. And the way it worked is that you only have one yellow box. And so when you got that signal to swap, what the kernel would do is there's a CPU instruction that says save all my registers onto the stack. And that's what it would do. So you got that interrupt, and then the operating system wants to schedule a different process. Well, it takes your context, which is the thing in yellow, that's why it's called a context switch. Your context is saved in memory. And then what it does is that it takes the other process, it has its context saved in memory from a previous invocation, and it will restore these saved registers into the CPU context, and then it will resume execution. So this is how the illusion is maintained.
And when you have like 4 processors, four of them, they just...
Oh, you're ahead of me by a slide. Load save registers and switch address spaces. Okay, I think the multiprocessor. So if you have multiple cores, which everything has multiple cores now, or if you do hyperthreading, then you have multiple contexts in hardware that you can then run multiple processes on simultaneously. So that's how that stuff is implemented. And so the idea of, so this is a multi-core implementation. You can think of a hyper-threaded or a shadow register implementation as being in this yellow box. You have multiple sets of registers, and it just switches back and forth between the processes that it has the registers for. Yeah.
Does that mean that other CPUs, like there's normally like a master CPU and then like child CPUs that actually do like say, hey, okay, we want you to do this one over here, or do this one? Like,
You can assign processes. There's this thing called processor affinity. So maybe I want my networking code. I have multiple processes running networking code or implementing the networking subsystem. Maybe I want those on the same core. So there is that you can do. Processor affinity is what that's called. Yeah.
Does it ever throw stuff in cache in the main memory? Like, it had enough time in between?
No. Clears the cache.
All right.
There's an instruction that clears the cache that invalidates it. Yeah.
So when we see our number of thread pathways, we call that to context switching.
Traditional, yeah. So if you typically only have one set of shadow registers, I can't go back and forth between three processes. I would, have to save a context into memory. Yeah. All right. So your example, if you want to get at the different processes that are running on your system, is to use a program called top, for example. This is the output of top. It's got different process IDs, the user who owns it. It's got the priority level. So these are run at the lowest priority. Your virtual memory space. So this is your allocated virtual memory space to your process. This is the amount of that virtual memory that's in real memory, that's resident. SHR, I don't even know what that is. And then the CPU and memory usage over time. So this is part of one of your binaries to use PS and to look at the different flags. So these flags tell you that these processes are schedulable, but there are other letters that determine statuses of processes, and that's going to be something that you will use your PS program for, yes.
How do you determine niceness or priority if both nice and priority are all the same value?
You can set these things. So by default, these are what you get, but then you can actually, in fact, one of your binaries set the priority level.
But it didn't. It was the same as everything else. I had to guess and find it out through other means.
Oh, maybe you're not set up for, okay.
Because these machines here don't have access to a lot.
So one of those levels that was supposed to be high priority ones didn't have a high priority?
No, it does have a
I
high
had to
priority.
guess and find it.
Okay, maybe on your, did you do it on a laptop?
Well, no, I mean, I think the SHR you have, so the largest value you have there.
Oh, the memory one for sure, but like,
No,
The
was a
SHR. So the larger number you have there, it means that you have lower priority, something like that. So because I found it in a forum, and it was saying that if that value is the highest, it means the lowest priority. So that's how I found it.
Yeah, I think
That's
I
new
had to do
to me.
something weird like that. I had to find it.
So this column didn't change for the high priority process.
Or it wasn't any of those. None of those processes.
Mine was 19.
Different.
Like it was.
Yours was minus 19?
No,
this one?
it was 0, 0, 0, and the one which was the lowest priority
19?
had 19.
Oh, okay.
And the rest
That's
was,
what, yeah, so then it does work on
Yeah.
Linux Lab?
Yeah, it was on a Linux lab.
Linux
I
lab,
don't know.
okay.
Maybe
All right.
my thing's just funky.
So this is one of your levels. I don't know if you guys have done it. Some of you have done it, but that's one of your levels. And this is the command that you would use to figure out the answer. Or so that level forks a whole bunch of processes with the same name. And you're going to use PS to figure out which one is, using the most memory, which one has the highest or lowest priority. And then there's another one, I forget what it was. What is running is consuming the most CPU is the other one.
And then there's one that's stopped, and there's one that's
One that's
a whole bunch
stopped, yeah. And that's to get you to sort of understand how to work with processes. So, all right. Question? Yep.
So within one cycle of the CPU, so in one cycle it executes something and then switches back to something else, or how
No, the
does
scheduling interval is on the order of milliseconds, which is a long time.
Okay.
That's a lot of execution for
So it's
CPU.
many cycles.
Yeah. You're typically every operating system is different, but yeah, typically the scheduling epoch is on the order of milliseconds, as far as I
Yeah, that's
know. Yeah.
It's still so fast. I never cease to be amazed by how fast all of this is.
Yeah. And it was milliseconds when I took operating systems. I don't know if they've changed that
I think it's
epoch.
nanoseconds, 10 to the 9.
Well, there is a... You don't want to do it too often because the overhead is you're clearing out the cache and you're switching into operating system code. So it wouldn't be nanoseconds. It would be, but
Millisecond.
yeah, milliseconds seems reasonable. But yeah, and typically, so like for video games, you need to run every 50 milliseconds. So it's at that granularity
Yeah.
that makes sense. A millisecond interval.
If you want like 60 frames per second, it's 16 and 2/3 millisecond per frame.
Yeah, so on dozens of milliseconds is where you would want the... Okay, so how do we control processes from our C program? That's what we're going to get to next. So as part of the C library, we've done things like get timers and do standard I/O and these sorts of things. What we're going to talk about now is how do I create processes and terminate processes from C. Terminating is easy. So basically, process can terminate using from one of 3 reasons, and there's only 2 listed there. I don't know why. Oh, well, this is the 3rd one there. One is receiving a signal whose default action is to terminate, like Control C, or you can explicitly say kill that process ID. Another one is returning from the main routine. So when your program ends, it'll exit the program, or you can call the libc call exit with some status, and this will terminate your process with this exit status of status. And the convention with exit is that status that you return is 0 if it's normal and non-zero if it's an error, and then the parent is going, or someone is going to catch that status code and do something with it, right? Okay. So exit is one of these functions that is called once but never returns. The instructions that come after an exit call never get executed. So that's the one thing. We'll see that it's different for other calls. The next call is creating a process. And the library call for doing so is the fork call. And the library call is the same as the system call. They're both called fork. This creates an identical process. So the parent is considered the one that issues the fork. And then it creates a child that's completely identical to itself, with the exception of one thing. And the only thing that's different between the child and the parent is the return value from this call. In the parent, the return value from a fork is the child's process ID, which is typically unique. And then in the child, the call returns 0. So fork will be called once, but returns twice. Once to the parent, once to the child. And then from there on, they're running identical code. Well, in the text segment, they're running identical code, aside from that one value. Okay. So up until now, we've done a sequential execution within the context of a single program. And most people can think sequentially much better than concurrently, which is too bad because almost all of the higher end programming now is being done with concurrent thinking in mind. So right off the bat, having you guys think about concurrent execution is helpful. So fork is providing you one of the coarsest forms of concurrency, and this is at the process level. I have to create an entirely new process with a separate address space. It's identical, but it's still a separate address space for implementing concurrency. Okay. So again, the entire process is identical except for that return value from the fork. In particular, the child is going to get the exact same file descriptors. So the parent and the child will share standard in and standard out, which are the I/O for the process. But when after the fork, if the parent and the child are modifying a variable x that has a value of 1, well, those changes to x are now independent from each other because they have completely different address spaces now. They're identical but separate. Okay. The other thing is after you do the fork, you cannot predict the execution order of the parent and the child. Because the scheduler is sitting there deciding, do I run the child, do I run the parent? And that is non-deterministic, who gets to run first. So you can't put any sort of ordering semantics after the fork. Yeah.
So that means that when the child gets to the fork, that any other processes that it calls will still be a child to it, right? So it's technically the parent, right?
You are the parent if you called a fork and have a child.
Yeah.
But then the child can also be a parent to its children.
So does that mean that the fork inside of the child, will that return still a 0, or will it return
within the child? So the child returns 0 off of the fork that spawned it. But then if it calls fork, it's now the parent. It will get a return value from its fork as the PID of its child.
So how does the child get a return value? Is it a argument to the overall process, or is it a...
I will get to that. Yeah, later.
So is it forking, like cloning? Like
Basically, cloning. Yep.
Okay.
Yep. Clone is a good word to use for that. Yes. Okay, so here's a call, fork 0. So the return value, if it's 0, this goes to the child. But if the return value is not 0, then it's the PID of the child. You say, I'm the parent. Simplest example. Okay. But there's an issue here. What about errors? I never check for errors. So typically, when we're calling fork, we want to do some error checking to actually make sure the parent and the child, or the child actually got spawned. For system calls, you do want to do some error handling, and this is for all the system calls. So I wanted to show you this code that catches the errors, because if the return value from fork is less than 0, and this is similar to the other system calls as well, if your return value is negative, that indicates an error condition, and you should look at the return value and then exit if you have an error, which is what this code does. And so typically you would put this in a wrapper and then use the wrapper everywhere you would call fork. So that's what this is. Here's a wrapper, so instead of calling the regular fork, I call capital F fork, and this thing implements the wrapper, or implements the error check, and then returns PID. And then everywhere where you would have used capital F fork, you would use this code, which would do your error handling. But of course, for brevity, I'm not gonna use this in my code, but this is what you should do, because these examples can get quite long if you use the other stuff. Okay, so fork example number 1. You have a program here that sets a local variable to 1. You call fork, and then the child is going to go through this part of the if statement, and it's going to print %d, which is a pre-incremented x. Otherwise, if you're the parent, you print out the pre-decremented x, and then both processes will execute this printf. So both processes will print, this is my PID, and x is currently whatever x ends up being. So when you do this, you see here parent has x equal to 0 because it pre-decremented its integer 1. And then it can come down here, and because its version of x is still 0, this is the parent printing out the last line. The child pre-increments and gets 2, and then because it has its own copy of x, it does a print with x equals to 2. The calls here that I didn't explain, the getPID call, this is a C library call that gets the process ID of whatever process is currently running, and that's also a system call. Yeah.
How does a child not recursively call fork?
How does a child not recursively called fork? This is not being recursively called though.
So, but when the child process starts, right? It starts in the very beginning of the.
It doesn't start at the beginning. It returns at exactly where the parent would return. So you copy the thread of execution also, right? So the parent executed this fork. When it returns, the fork returns twice, one for the parent and one for the child. Now both the parent and the child are right here on this if statement.
Okay, that makes sense.
So the instruction pointer got cloned.
I thought it cloned and then started from the beginning.
No, it did not re-execute.
Not
Yes.
from
Yes.
the same spot. Okay,
Yep.
that makes more sense.
And in what context would you want for?
Like if you're a shell, so I'm a shell program, you type ls, I'm like, well, I don't implement ls. I'm bin bash, not bin ls. So it creates a fork of itself. It says, oh, okay, fork a process, and then it's going to do a call called exec, which says load a new binary up into my address space. That's how, and I'll talk about exec later. Yeah.
So the system is tracking parent-child relationships between processes.
Yes, I'll get to that. Yeah, because you see this PPID, get parent process ID. That says, who's your parent? I got to talk to them. That's what that thing is. All right.
Your bad process.
Yeah, you've been a bad process. I got to talk to your parents. That's what that is. Okay, so when you do these fork examples, it's really hard to process them unless you're doing it visually. You need the visual aid to figure out threads of execution, and that's what I'm going to talk about next. And for any of these things that you see on exams, draw it out. Draw out exactly what's going on, and you'll be much happier when you're reasoning about these things. So the graph visualization, what I'm going to show you is a way to visualize the execution of this code using a graphical method where time is on the x-axis. Vertical lines are fork calls that will spawn children, and the child is always on the y-axis, we'll say, just as convention. So here is an example of how you would use this. You start the program, it only has one thread of execution, and the variable x is 1. You hit this fork, and this is what you should do visually, is throw up the child, send it up on the next line, and then the parent continues. And then the child is here, so now you can say child has x is equal to, and then x is now 2, and the parent has x is equal to 0. And then what happens is they continue with this call down here, and so this is allowing you to keep the variables straight, because there's two versions of x, and they have different sort of values. Doing this graphically allows you to separate what's going on. Okay. So here's an example. There's two forks now. And this is where you can see that throwing things up graphically will help you. So what we're going to do is we're going to start fork 2. It's going to print L0. So L0 gets printed once. You call fork. Now you have a parent and a child. And both the parent and the child are here at L1, so they both print L1. But now, both the parent and the child call another fork. So graphically, you want to do something like this. So both the parent and the child spawn another child, and then you do a printf of by, so you can see that by gets printed 4 times from this. Okay. So this is how you sort of try and reason about concurrency, because otherwise it turns into a mess. Well, unless you can think differently. So personally, I have difficulty with keeping it straight. So again, here's another level of fork. Now you have 3 forks. So you have L0, it spawns off L1, and then L1s each spawn off L2s, and then L2s spawn off L3, spawn off processes, and they all print by, so you get by printed 8 times here. Yeah. So you guys have heard of fork bombs? This was a way of being able to crash a Unix system in the 70s and the 80s. You would call fork in a loop and then take up all of the operating system's process address spaces. Like the PID space is like 32, is it a short? It used to be a short integer. And so it wouldn't take you long to basically consume all the PIDs on your operating system. Before they put quotas, and they got smart about it. Okay, so here's a more complicated example, and this will really show you the methodology for tracking forks and graphically. So fork 4, so you start with a printf of L0. You do a fork, but then if you look, the child is going to immediately print by, right? Because the return value for fork is not equal to 0 only for the parent. So then you're going to throw up the child and immediately print by, and the parent's going to continue. So that's what this is. Now the parent is here, and the parent, sorry, I should do this on the video. The parent is now here. It prints L1. The child terminated, right? So it printed by and left. But it calls fork, and now its child is now going to go to by. And then the parent is going to continue. So that's what that does. So that child is now hitting this by. So the final parent, the original parent finally does prints L2, and then it calls fork again. And after it calls this fork, both the parent and child of this fork will return here, and then they will both print by. So this is what you get. Yeah, 4 bys. Yeah. Questions? Okay. Here's an example where the fork is in the child. Start with L0. On the fork, the upper branch is the one that continues, and the lower branch now exits out with a by. And then the child will print L1 and then do another fork, and its child will continue, but the original process will hit by. And then finally, after you print L2, you do another fork, and then you have 2 more bys. Okay. Do I have an example for you? Oh, there's the example. All right. One last thing is the @exit call. One of the things you can do in C is register a callback that says, when you hit the exit function, I want you to execute the cleanup call. So if you do something like this, register and this is sort of like a handler, like an exception handler. When you execute this instruction, this registers the handler. The fork will spawn both a parent, will spawn a child, and both the parent and the child will call exit. And because the address space is shared, the callback is also shared, right? You registered it in the parent, so when you fork on the child exit, the child is also going to call the same cleanup code. So this is what it looks like. You have the fork, and then with the fork, after the fork, they will both execute the cleanup call. Okay, so now let's do practice problem 8.2. Consider the following program. You set up this variable to 1, you do a fork. Wait, is that the exact same example? No, slightly different. Yeah, slightly different. So yeah, what is the output of the child process? And what is the output of the parent process? And if you want to, you can use the visual. Here's some more scrap paper here. Okay, so for the child process, it actually hits this printf1 because the return value for fork is 0. And then it pre-increments x. So it will printf1 x is equal to 2. And then it will, after this if loop, it will call printf2, and then it will pre-decrement x. And when it pre-decrements x, it returns you 1. The parent, on the other hand, immediately goes to this printf2, and so it will print out x is equal to 0. All right, here's were there any questions about this? Straightforward. Here's another practice problem. How many hello output lines does this program print? And yeah, for this one, I would keep track of your integer I in your graph. So use the graph, and then keep track of integer I, and then see what you get. So for the I equals 0 iteration, you execute this fork once, creates 2 processes, and then you go through this loop again with 2 processes, but now I is equal to 1. So then when you do this fork, now you have 4 processes, and then you increment I again, but then you fall out of the loop. So then it is 4.
So that's exponential.
Mm-hmm. That's why this in a loop will bring a Unix system to its knees.
Especially if you do or a while true.
Yeah, while true. Yeah.
My for command.
Yeah.
While true fork.
Yeah. Don't do it on a Linux lab machine. Well, I think the maximum number of processes is like 64 by default.
But they notice. I'm pretty sure they have a thing to check to see if you're for that.
Oh yeah. Well, you could test it. See how good it is.
Send you an angry email.
We got you credit for it.
No. All right, here's practice problem 812. How many hello output lines does this program print? So it is 8. So when you call do it, there's only 1 thread of execution here. When you call fork, there then becomes 2. When both of those call fork, you then have 4. So now you have 4 processes that are right here. All 4 print hello. All 4 return. All 4 print hello again. And then all 4 exit.
So the fork is forking. The fork is forking the fork. Like in
Yes,
doing.
it forks itself.
Yeah.
Indeed.
Okay.
Okay, a full process.
I just got the other
Correct.
That's a fair thing.
The 4, yeah. No, that's not. There's not 3.
No. I was just thinking that the fork before that is forking that fork.
Okay. Oh, the fork is
It's
forking
forking.
that. Okay, yeah. You're right. You're right. Correct.
This is why you have child processes and parent processes. So you don't see
Yeah, but then when the child is a parent in the next generation, then you're like, well, which one did you want?
It's the child. It's the second generation.
Yeah. Yeah, generation numbers, yeah. Okay, so when a child process terminates, it typically sticks around because it wants to stick around for its parent. Because if it dies, it wants to be able to make sure the parent knows why it died. And until the parent finds out why it dies, the child sticks around as a zombie. So that's
I love computer science.
that's how Unix works. So the child will keep its exit status in particular. This is the one piece of information that it needs to give to the parent. And it needs to be able to deliver that. So it's basically a living corpse, half alive and half dead. And so the parent must reap the terminated child. I used to say clean up after its children rather than dying and notifying, but I
This will
think
stay,
that...
my friend.
You stay, yeah. Typically, the shock emotional value is what will get people to remember things.
This is one of those things you're not going to forget all the time.
Pretty much. So,
Are these standardized terms?
yeah,
No,
actually,
actually,
well,
reaping.
not standardized, but a lot of people use the reaping of yeah.
I've heard zombie before too.
Zombies are, yeah.
So how does it return that to its parent if it doesn't have a return? Like, how is the parent going to actually see the return code of the child?
With a wait or a wait pid, in fact. So there are special library calls for the parent to call that says, check up on the child. And that's what wait is. The wait and the wait pid calls say, hey, I forked off a child and I haven't heard back. Let me do a wait on that child and figure out what the status was.
Does that return that PID to the parent, or return the exit status?
It returns the exit status of the child that terminated. Yeah.
So that's a way to help take concurrency and force dependency.
Yes, which will be some problems later on. Yes, there's a way to force sequential execution. Doing so. So as soon as the parent reaps the child by calling wait, then the kernel will finally get rid of the child process. We'll completely clean it up. Okay, what happens if the parent doesn't clean up? Doesn't care about what the child does? Well, this child zombie will stick around until the parent dies. And when the parent dies, the origin process, the init process, process number 1 on Unix, that will reap that orphaned child, basically. So, yeah. So that's how processes work, waiting on processes. So here's an example. Fork 7, I do a fork, and the child will immediately terminate, call exit, and then the parent is going to sit here and do nothing. It'll just completely ignore the child. And then if you run this, and you do a PS listing, you will see something here. The parent is sitting here happily consuming all of your CPU with this infinite loop. And the child, you see the PID is 6640. The child is here defunct, which is the zombie process. Yeah.
So when you have a cleanup, when you have that cleanup function that you found earlier, does that happen when the child terminates, or does that happen once it's reaped?
When it terminates. Yeah, when it terminates.
So it'll actually, like if you had a printout statement or something like that, it'd print out before
Yeah.
it was reaped.
Because it's the next thing that happens after you reap is the kernel just deletes the...
Memory.
Yeah, it doesn't pass control back into the child.
Okay.
So, from another point of view, would like forking create memory leaks? If you have many things that they are not running, but they're there and out, memory has been allocated.
Well, hopefully when you do a fork, you're intentionally creating a process that you need.
Okay.
Yeah, that's the idea. And then so now it's the zombie, and later on when you kill the parent, you'll see that both the parent and the child are gone. The init process cleaned up the child. Okay, here's a non-terminating child example. Here, the child fork, the child part will go into the infinite loop, and then the parent will immediately terminate. And so if you run this, because the child is still running and the parent terminates, the parent, because it terminates, it can actually exit. It doesn't have to wait around for the child if it is exiting itself. And so this is what you get. The parent terminates, the child is still around here, and then when you kill the child, the init process will reap the child because the parent is no longer around.
So when you call program on Linux box, is it actually the init function that is parent for all of those?
So the init process is the parent to a whole bunch of other processes that get spawned. So in the init sequence, that's the ancestor. That's the, what is it? Our ancestor in Africa, what's she called? Jane?
Yeah.
Or Lucy. So init is Lucy. And Lucy spawns off a lot of the system processes, and then those things will spawn off like servers. And then from servers, you have your interactive, maybe your login and your shell. And then from the shell, so you have this tree.
And basically that's system D now for most people.
Yeah, if it's not, so systemd is, so init will spawn off systemd, or there might be some processes in between that.
System D now runs init for a lot of people.
Oh, okay. Not me, though, because I don't think I need systemd. Then I have to relearn a whole new set of things. But anyway, there's this ps tree command that you can see the hierarchy. That's not a level in your CTF, but that's the command if you want.
And you have all
I
these
found
errors,
that.
Yeah, the ps tree command. Yeah, if you're interested in who is responsible for who.
One of the ways that I didn't have that cool command that you showed us.
It's the paternity test.
Did you say it runs as PID 1 or 0?
1, I believe. Yeah, 1.
It's not the system D spawns init, system D replaces init entirely.
Okay. Okay, all the sysv stuff is gone. Okay. Is that default now on
Pretty much everything, actually.
everything? All right. They swapped over. Oh, H top. All right, I will update my slides.
That's like the top command, but it's like interactive.
Hierarchical.
Put it in the tree.
H top has colors.
Also,
All right,
That's the real.
I'll put that on there. Maybe I can actually do a level that's got H top in it. Okay, so let's get to this wait call. The parent will reap a child by calling this function, and then it passes as a parameter a pointer to an integer that will store the status from the child. All right. Okay, so the return value of the PID, the return value of wait is the PID of the child that delivered the status, a particular status. So there are two pieces of information that need to get passed back here. It's both the status code that the child is giving you and the PID of the child itself. And so for that reason, the return value for wait is the PID, and then you have to pass a pointer for wait to fill in the status. So that's the structure of this call. All right. So here is an example. You have a fork, and the child will print hello, and then we'll print bye, and then we'll exit. And the parent will print hello from the parent, and then we'll wait for the child. And so it's going to wait and read the status into the child status variable, and then print off child has terminated and bye. So this is exactly what Sean was referring to. Now you can enforce a little bit of ordering between instructions that the child is executing and those that the parent are executing. So this is where the graphical part helps you. So you start off here, you do the fork, and now the child is up here at HC, and the parent is down here. And then the parent now is blocked. The parent cannot continue until the child completely finishes. So now you can go over to the child and finish off the child, and the child is going to, after doing this printf, is going to go down here and print bye, and then it's going to exit, and when it exits, it can then hit trigger in the parent the return of this wait call. And then after that wait call has returned, you can print the child is terminated, and then the parent is going to hit bye. So here's an example of a routine in which you have an array of PIDs, and for the dimension of capital N, and for I from 0 to capital N, you're going to set the return value of the fork to the element in that PID array. So what this is doing is inside the parent is keeping track of the PID of every single child that it has spawned off. And then if this returns a 0, meaning that you're in the child is now going to exit with a status code of 100 plus whichever child it is, from I to N, from 0 to N. So this is going to immediately cause each child to exit, and then the parent is going to spawn, or it's going to do a wait on all of the children sequentially. So from 0 to N, it's going to call wait to get the status code of each child. And in order to get the status code, there are two macros that you need to use. If exited on this child status will return whether or not the child has exited normally. So if this is true, that means the child terminated normally. And if the child terminated normally, then you can get its exit status as exit status child status. And these are just macros that help process the return value of wait better. Yeah. So in this case, for 0 to N, I'm just going to wait N minus 1 times, or N times, sorry. And then I'm going to print out this child has terminated with this specific exit status. If it turns out the child aborted, if it terminated abnormally, so if someone sent it a kill signal, the exit status would be an error status. That's what you would get instead if that child exited without doing a normal return. So if you execute this, you'll get this output. And one of the things you should notice is that the interleaving is random, right? It is not the case that the first child that you spawn, 100, is the first one that's terminating in this wait. So the wait is always going to get to the very first child that terminates. And sometimes that isn't always the first child that was created. So there is no ordering as soon as you spawn off the forks. And that's what this example is trying to show you.
The parent's always going to be the last
That's
one.
because of the scheduler.
Yeah, the parent's always going to be the last one, and it is because of the scheduler that you don't know the interleaving.
And that's because of the wait.
This wait, it says, give me the first one. And then that's the PID that terminated first. Yeah.
So that also means that every single child of and is also spawning their number is up to n number of forks as well, right?
No, because after the child is spawned, it immediately exits, so the child never forks.
Oh, that's right.
Yeah.
Sorry, I'm trying to get used to reading that.
But there's a sequential child gets spawned, and it's a sequential all the waits. It's the middle part where it gets messed up.
Well, yeah, I'm still trying to get used to reading the forks inside the code and being like, oh, that's where it's starting, and now it's going.
Yeah,
there.
the child starts right there and then doesn't exit.
So if we did something like an assignment, because you can do some funky things in C by putting in things like, oh, this.
You can put an assignment here and then return.
You can put an assignment inside your for loop.
Yep.
So, or like in the declaration of your for loop. With newer versions of C, anyways. I just trying to think through.
All right, so the original wait will wait on any child process that is returned. If you want to wait on a specific child to return, then you can use the wait PID call. And as a part of the wait PID call, you give it the PID the child PID that you want to wait on. All right. So and it's similar. It takes a status, and then there are some options that you can also pass it. But we'll for now set the options to 0. And so in this case, you do again sequential spawning. But then what you do is, in this loop, you go from the last child that got spawned to the first child, and you sequentially wait on those PIDs in order. So then what you get is, so this was the original one. It returns in any order, 103, 102, 101, 100, and then the one that we just saw does it in reverse order. All right, so practice problem 8.3. Consider the following program. List all possible output sequences of this program. So this will get you the idea of which things can be interleaved and which things have to have a strict ordering in order to execute. This wait PID of -1 is the same as a regular wait. Sorry. Yeah, in fact, I should have put that in there. Write that down.
By enumeration.
All the different sequences. So, for example, I overheard the A and the B can be in any order because the fork happens, and whether or not the child runs first or the parent runs first, up to the scheduler. You don't have any control. After this printf of A, in fact, the child could even printf C if it wanted to. And so the first 3 letters, A, B, and C, well, definitely the A has to come before this C. In fact, the A has to come before both C's, as it turns out. But the B and the A could be in any order. And then that last C, there has to be a C at the very end. So this is the way you can sort of reason about it. So you can do child first, and then parent, and then the child C, and then the parent C. That's what this sequence is. You could have the parent go first, and then the child has to do both A and C before then the parent can get this last C. Or you can have the child run to completion doing A, C, and then the parent does B and then C. The sequence you can't have is B followed by C, because in order for this to happen, the next C either has to have an A in front of it. Well, it definitely has to have an A in front of it, because then you're blocked on this wait PID. So, all right. So here's another one. Consider the following program. How many output lines does this generate, and what is one possible ordering of these output lines? Only one, not every one. Just give me one. Okay, so the number of output lines, this gets called once. After the fork, this gets called twice. Then the parent is going to now do the wait, and as soon as the wait returns, assuming that it was a normal return or a normal exit, we'll print another line. So now this gets printed once. Then both the parent and the child will print that. So actually, before this can be printed, the child has to print by, and then the parent will print both this line and that line.
So
Okay.
6 lines.
6 lines. Okay, so one possible ordering. Well, you always start with a fork. You always start with the hello, and then you could either do the parent or the child, so 0 or 1, but then the child has to hit by. And then when the child returns, it's going to return a status code of 2. So on this wait PID, the status will have 2, and that's what you print out. So then you print 2 in the parent, and then the parent will then print by, and the parent itself will return 2 to its parent.
Well, wouldn't that be a bad code in normal? Like exit 2 would not be normally a good exit.
Yeah, it's a not so good exit, unless it's a problem in a practice.
So something, yeah, isn't non-zero like bad news?
Yeah, non-zero bad news in exit codes. Yep. Okay, another, so that's fork and wait. Some other methods of interest are sleep and pause. Sleep will suspend your the running process for a specified period of time. One of the things with sleep is that you can be woken up prematurely. So if you get the wake-up signal from another process, you're going to wake up and you're not going to have gotten your rest, enough sleep. So that's the semantic of the sleep call. When you return from sleep, you should always check. If it matters, you should always check to see how much you slept. Yeah.
Is that something that like when you wait like non-deterministically for like some sort of signal from another program, is that what it actually enters as sleep?
No, that's what pause is. Pause says suspend. I have nothing to do right now, so I'm gonna pause running, and then wait until someone sends me a signal to wake up, or sends me some signal that forces me to wait to process the event, and then it'll wake up. So that's what pause is. Okay. So I am going to just walk through this. So this is practice problem 8.5. Write a wrapper function for sleep called snooze that behaves exactly as sleep but prints out a message describing how long the process actually slept. So here is the return code. The return value for sleep is the number of seconds you actually slept. So what snooze does is it calls the sleep and then returns the amount that it intended to sleep minus the amount that it actually slept. Oh wait, no, it returns RC and then it prints out the amount that it had left to sleep. So, all right. Okay, so with fork, we have figured out how to create an identical copy of a specific process, but it would be terribly inefficient to write, if you have 5 different processes that you wanted to write logic for, and each one was different, it would be tough to monolithically write that and then have fork sort of figure out which code path to execute. So if you have processes that that are sort of independent and that should have independent, completely different address spaces, then to spawn one, then you would use the execve system call. And what execve does is it takes your current process and it completely wipes it out. And it forces a load of a new program, a new program in the file system, and it will load up and create a new instance of that program. So it'll create that a replacement process. So the arguments for execve is the file name in the file system of the binary you want to execute, and then the arguments that you want to send that binary, just like in the shell, you're passing the program arguments in argv. Similarly, when you want to call it from C, you also have to give the arguments programmatically, and these will typically be strings as well. And then your environment. So you can pass your environment variables into the binary. Now the shell is going to do this for you automatically, but if you want to spawn a new program from C, then you have to set that up, your environment, if you care about it. You have to set that up programmatically. So environment variables like your shell, the name of your shell, the current working directory, those are things that you would have to set up. Okay, so when you do the exec, it's going to overwrite the code in memory. All your memory segments will get wiped out. The data, the stack, everything gets wiped out and loaded fresh from with the new process. The only thing you retain is your process ID, and then the open files and the signal context. Yeah.
Is there a variation of this process that opens up and returns back the original?
No, it would be brand new. If you fork and exec the original program, you would get
The same result.
the same result. But then it would start at the beginning. Then it would start at the beginning of that that original process, right? Because when you do a fork, you're somewhere in the middle, wherever that fork was. But if you do a fork and exec of the exact same thing, then you'll start at the beginning of that program.
Or like
That
an exec
is
for
how
another
a fork
program.
bomb works.
Yeah, you
If you
can.
needed that other program to work first, couldn't you just do a wait on that? On the parent? Until the child's done doing its stuff with the other program and then get back to your program?
If you wanted to implement something like that, sure. Yeah, you could.
So how does this transfer control? Because all this does is create a child that's an exact copy of you, right?
This is going to replace your entire memory space. This is like loading a new binary into your process address space.
Oh, so you're
You're calling the loader again.
yeah, okay, so
Right.
it kind of considers your program as being like the predecessor. It's kind of like a prepping way.
Mm-hmm. Okay, so exec is interesting because it's called once, never returns. After the exec finishes, no instructions after that will execute because you completely transferred execution to a new binary. So that's the endpoint. That's the end of that. So in the original program, that's the end of it. End of execution. Unless there's an error. So actually, after the exec should be the error handling check, because then you're definitely in an error condition when you tried to do an exec and it didn't actually return to you. Yeah. Okay, this is what it looks like when you set up a process to do an exec. So this is for example, the command that you want to exec is bin ls with these arguments. What you would want to do on the stack before you call execve is create an argv array and an environment array. And the argv array has bin ls as the first string, the -lt as the first argument, and the user include as the second, and then a null to indicate the end of this array. So you're setting up your own argv to pass to execve, and then you do the same with all your environment variables. You can pull these from your own process's environment variable space. It's just sitting there in memory with this special name. And then you would copy that over, and then you could call execve with the parameters that you wanted. So that's how it works. This is how it's implemented. So the way the stack works is when you load a program, the first thing that gets put onto the stack is the environment variables, the strings associated with your environment variables, and then the strings associated with your command line arguments. And then finally, the pointer arrays for both the environment and for argv are placed onto the stack. And then argv points to the beginning of that array. Finally, the stack frame for main, or the libc start main, is put onto the stack. Well, there's a bunch of other stuff in gray. And then the last thing is the future stack frame for main. And this is where, after the loader runs and puts all of this on the stack, this is where transfer finally gets over to user code. And then from here, all of your stack locations that you've been working with in this class are below this. So that's the structure of the stack as you're invoking a program. Yeah.
So anytime you're looking above whatever main's root base pointer is, that's normally looking at either an environment variable or an argv.
Yep. Yep.
And where is the PLT table?
It's all the way down in the sort of the data, the .data section.
Okay.
This is in the stack. So.
And this whole thing is a stack frame, or?
Well, no. This is the whole stack. This is the bottom of the stack. Stack frames that we're talking about for function calls are sitting here towards the bottom. So by the time you enter main, all of this is on the stack.
Okay.
And then this is how you get your pointers to argv, and then argv of 0 pointing to the actual string. Those are all pre-allocated ahead of time before you enter main. So that's how it all connects up. Here is a program that will print out both your arguments, which you've seen this one before, and your environment variables. So just to show you, like you could run that, you could compile this and run this on Linux Lab. But I'm going to skip it. And I'm going to, 336. I think I will stop and just take questions.
So how is it? How is the execv returning an error state if it's already over the stack?
If the execv call, for example, can't open the file, where is this? Yeah.
The execv is actually.
Yeah, if the execve can't open the file, this will actually return.
That's an error from execv.
Yeah, if it can't, and then this will pass back an error code that will be negative. And so you see the way this code is written is if execve, the return value of that is less than 0. If it's successful, you'll never get to this. But if it, for some reason, for example, I can't find that command to exec, then you'll come in here, command not found. So if you imagine the shell, when you enter a bogus command in the shell, it says command not found. That's because after it tried to do an execve on that command, it got the from the system.
So it's always gonna do error checking before it wipes out your stack.
Your shell would, yeah, but you should too. Oh no, yeah, it will never wipe out the stack if it fails. That's true. But you should definitely check to make sure that the return value is there.
But it returns only if it doesn't work.
Yes, only if it doesn't work.
So the function itself actually does have a return. It's just when you run the function, if it does work, it never gets there.
Yeah, so this actually might be redundant. You could just do execve of that, and then the next thing could be printf.
Probably don't even want to.
Command not found. Or actually, there might be different ways.
Or no.
Yeah, there could be other things that have gone on, but yeah.
So I just installed Maven, and that's what this is doing. It's like something for Java to help you compile stuff off Git. And I had to go in and change all these environment variables on Windows so it could find all these targets. So it'll launch JK, and then it's going to exec command with this Maven overlay, and it's going to paste them together, right? That's kind of what's happening.
I would imagine, yeah. So a lot of programs require environment variables to be set specifically.
Right.
Yeah.
It took hours.
Yeah.
It's a weird one.
Yeah.
So good build environments will set them all the time for you so that you don't have to worry about that. But yeah, one of the things is if you install something in one directory and all of a sudden move it and expect it to be able to run in a different one, yeah, because the variables are set specifically for that location. Yeah.
So we've talked about fork, which spawned a clone of our copy of us. We have exec, which is a whole other process itself. Can we spawn processes that are not part of our own like code base, but is a whole other like application out of ourselves and run concurrent with ours?
That's what exec would be. You would exec a different part of your application suite. So I'm imagining something like LibreOffice that's got the writer, it's got the slides, and then maybe it would invoke a different.
And so what it does is it spawns a child process with a special exec for that child, right?
Yes.
And then that one probably.
So like when you do a new document, and then all of a sudden you say, "Oh, I want a spreadsheet," and then when you click on that, it would know within its suite that it's got a separate program for the spreadsheet. Would be an exec, yeah. And then when you do a process, you could see this when you do a process listing, and you see either Libre Writer or Libre Impress is what it's called for the presentations, or Libre Calc.
Yeah, there we go.
Then that's what it's doing.
Okay. So you have to still like natively inside of Linux, we don't have anything that just spawns a specific process and continues executing on it.
Well, so the shell does that. In fact, the very first example in next class is a shell that you can background commands in, right? Like, how does that work? Where I can, if you guys know the and sign, if you type like Firefox with the and, it like backgrounds Firefox and then returns to the shell. That's what you're thinking of. No?
Maybe.
How does that work? That's what we're going to talk about later.
Oh, that's a process.
Yeah,
That's more what I was
backgrounding
talking about.
processes. Wait.
Like how to spawn a concurrent process.
So like if I have a specific function that I need to have run, and maybe I need to spawn off a couple others that do a bunch of concurrent processes on something, but I want to do like, I need to do like maybe I'm making a game. I want my graphics engine to start running. I want my user input stuff to start running. I want to be able to start processing different, like essentially sub applications.
If they require the same memory space, then you will want to thread that application, which I have not talked about.
Okay, so
Because the
threading
courses, that's a finer grained way of getting concurrency and parallelism. This is super coarse, the fork and exec. Typically,
Oh, those
you
are
would
good.
use process level concurrency to, just like in shells, they're completely independent. Typically, when you're using process level concurrency, they have to have almost completely separate logic. Like, yeah, I want the word processor here and the spreadsheet here. Separate processes, separate code that they're usually executing.
Okay.
But if it's something like a video game, and I need concurrency in the video game, I need multiple threads operating in the same address space, yeah, that's threading that you would use that for. Which, this will be better. This will be clearer in operating systems when you talk about that, concurrency models.
So do that when you just like work a child, like exactly
For threading, there's the threading libraries like pthread and what do you mean by a concurrent program?
So you like let's say I wanted to run a shell parallel to